Hello, programming languages students. Welcome back to another grammars slide here, grammars video. So here we're going to talk about the transition from automata to grammar. So given an automata, how can you write a grammar for it? And we'll see pretty quickly that it's really easy. And if you do want a challenge or something interesting from this process, it's in how can I simplify the rules? Um, and so let's start talking about this. So let's say we have an automata. It's drawn out. We have states. We have transitions. Well, states we can consider non-terminals or rules in a grammar and directly translate them. So if you have a state, give it a label. That label is now the label for the rule in the grammar. The alphabet letters, the transitions, are same as terminal characters. So if you have a transition with like a lowercase a, this now becomes just a lowercase a in our rule. The start state of our automata is just the start symbol in our grammar. So the letter S starts where the automata starts. And then the last rule that makes this easy is that any final or acceptor states have, in our grammar, have just a lambda as an option because that allows us to terminate our string. They're basically terminal states. So let's actually look at this in practice. All right, so here's an automata. I don't know what this automata does. I drew it a long time ago. I don't remember exactly what it's producing. It seems something like an odd number of A's, maybe gets there plus either a lambda or two b's at the end. I don't know. There's a couple ways we could potentially look at this. But you know what? It's not important. What is important is that um, and there's I don't know the looping a and q1's got me thinking. Anyways, it doesn't matter. The automata does a thing. It has a set of rules. We don't really care. For the transition to a grammar, it doesn't matter. We just label each state. So q0 is S, q1 is A, q2 is B, and q3 is C. So we've now labeled each state, and we're going to use these labels with our rules down below. So we have a rule for S, a rule for A, a rule for B, and a rule for C. So for each state, look at all the out arcs. How do we transition? Well, from state S, how do we transition out? Well, with a lowercase a, we transition to state A. Lowercase a, capital A. From state A, what are our out arcs? Well, lowercase a gets us to S. Lowercase a also gets us to A. Lowercase b gets us to capital B. Or we have a lambda transition that gets us to C. So in other words, just C. So that's it. That's all the out arcs for our A um, state. For our B state, what are the out arcs? Well, we have one out arc, which is a lowercase b that gets us to C. And then it's also important that this state is a final state, is an acceptor state, and so we add a lambda as an option. And then for state C, we add a lambda as an option. So these grammar rules will produce the exact same language as this automata. Simple as converting and figuring out where the out arcs are and how to write them out. So why don't you try giving it a shot? So given this automata, write a grammar rule, set of grammar rules for it. So I'll let you guys have a chance to pause the video, give you about 5 seconds of silence here, and then we'll talk about the solution. Okay, so the solution to this, if we follow our rules defined above, is we have our starting state, which can loop into itself with an A. We'll call this S. We'll call Q1A, Q2B, Q3C, and Q4D. Um, so we can loop back in with an S. With a B, we go to state A. With an A, we go to state B. From state A, an A goes to state B. From state B, B goes to state C. An A goes to state C, B, C, A, C. And an A goes back into B. So A, B, A, C, A, B. Or sorry. A, B, A, C, or B, C. All of these are options. From state C, we have a single B that gets us to state D. State D is in our acceptor state, so it has a lambda. And it also can loop back into itself with a lowercase b. So lowercase b goes back into D. So there you have it. That's it. These grammar rules would work. Now, let's do one other thing. This is a pretty simple process. Let's look at this automata below. Do one more set of production rules, get one more piece of practice here, and think about after you write the rules, think about substitutions and potentially how you could produce the same output, but maybe get rid of a state. Maybe there's not a need for at least one of the states here. Um, maybe because, and in particular, the hint I will give you is that grammars can have multiple letters in a transition. So maybe there's a state that we can get rid of here by using that hint. So I'll pause. I guess I'll be silent for a couple seconds here and let you pause the video and get your attempt in. All right, let's talk about it. So you'll notice we have 5 states, but we only have 4 rules. So how did we do it? Well, from state S, we can loop back into state S with an A, and I did not call Q0 state A. I called Q2 state A because Q0 is not really needed. With a grammar, we can say lowercase a sends us to state Q2. We don't need lowercase a to state Q1 and then lowercase a to state Q2. We could just do 2 A's, gets us straight to Q2. So it's like we drew an arc with AA on the arc. So A sends us to S, AA sends us to Q0, which is A, label A here. Or with a lambda, we can transition to label A. It's our choice, either 2 A's or a lambda. Then from state A, we can loop back in with a B or go to state B with an A. And then from state B, which is Q3, going to state C, which is Q4, we need a lowercase b. Oh, and by the way, there's a way to get rid of state B as well, or the state as well. There's a way to write this with 3 production rules. See if you can find it real quick. Well, the trick is, again, if you're just transitioning with an A and then a B, why not get rid of this rule and just have transition from A with an AB to state C? So we could really write this with 3 rules. We could get rid of Q1 and instead use 2 A's in a row. We could get rid of Q3 and instead replace it with literally AB. So we can actually get rid of 2 of the states. So then once we make it to our final state here, an A loops us back in, a B loops us back in, or a lambda because it's an acceptor state. So hopefully that makes sense. Let's see if you can do one more simplification task. In general, this is preferred but not required for grammars, so it's a nice thing to be able to do, and we're programmers, we like to be efficient. So similar automata to the one we just looked at, but with a few different tweaks to it. See if you can write this with only 3 total production rules, a rule S, a rule A, and a rule B. I'll give you 5 seconds to pause the video and get your attempt in, and then we'll really quickly go over the answer. All right, so hopefully you ended up with something like this. From state S, we loop back in with A. We could also go with BA to state A, or A to state A. From state A, we can loop in with an A. Oh, this should say lowercase a, capital A. I will fix that in the slides before you see them, but I don't want to re-record this whole video. So this will be a lowercase a, capital A. And then an AB gets us to state B, or a BB gets us to state B. So either AB or BB will get us to our final state here, and our final state loops back in with a B or has a lambda. So that's it. Honestly, the simplification for grammars, again, it's not required, but it is nice. It gives you nicer looking outputs. What I would recommend is just, for now, to be safe, in the assignments, just use our basic rules. Label a state, label the out arcs to the next state. It'll make it easier for me to check, and it's not really necessary to simplify, although it is kind of a fun task. So whichever way you choose is totally fine. It's up to you. But we have one more grammars video, so I'll see you next time.